folks, I'm going to look at a very, very interesting geometric sequence question, actually a sequence question. There's two of them. The one is a brilliant application of sequences and series like we saw in the previous one with the steps. Then there's a quadratic equation that's quite interesting the way they've asked that one. So I'm going to start with the application, then I've got another application for you on the calculus that we will look at as well. So let me just draw this diagram that they give us in the book. I'm just going to draw it more or less up to there. They say the following. This is a piece of paper. The paper is A, B, C, and D. Okay. This is 21 centimeters. Each one of these blocks is a centimeter high. But now there's a catch. They do not use all the blocks. This piece of paper is 36 or 30? No, it's 30 centimeters high. Okay, so each second one of these strips are not used. So that one isn't used, that one isn't used, that one isn't used. So you can just think if these are all 1 centimeter big, we're actually using a space of 15 centimeters on this page. Now what makes this interesting is the following. They say, rectangles of width 1 centimeter are drawn from the edge of a sheet of paper that's 30 centimeters high and 20 centimeters wide. Now each consecutive rectangle is 85% of the length of the previous one. So if this is the first length that we've got, which is this 21, this is 85%. So 0.85 times that length. So we're only going to use this part. So look, as you'll see, once we draw it, it looks like a graph, a bar graph. Okay, then the next one will be 85% of this. Okay, so let me write this down. The area of strip 1 is simply just 21 times 1, which is 21. The area of the second strip, in other words, that component, is 85% of the first strip's area, or length rather, that we're using. Okay, so this length here, now it doesn't matter if we use length or area because the other dimension is going to be 1. So let me just make sure what are we working with the length. Now they are going to ask us for the length of the 10th rectangle. So let's just change this A into an L. Okay, so we've got length 1. Length 2 is going to be 85%. So 85% translates into a factor of 0.85. Just divide it by 100. Of that 21 is length 2. Now I'm deliberately not multiplying it out so that you can see what is happening, how this is changing from one length to the next. So length 3 will be 85% of that. So 0.85 times this, which is 0.85 times 21. So this becomes 0.85 squared times 21. Length 4 will then be 0.85 of that. So it's going to become 0.85 to the power of 3 times 21. And that's enough for you to notice what the actual pattern is in this little sequence of ours, sequence of lengths. Okay? If it's 2, the number 2, the power is 1. If the number of the block that we're looking at is 3, the power is 2. If the number is 4, the power is 3. Always one less. So you can immediately then conclude that the length of the 10th strip is going to be 9 of these 0.85s. That's multiplied by 21. Okay, and if you want to work that out, it is approximately 4,87 centimeters, and that's correct to 2 decimal places. Okay, now the question number 2. So that was for 3 marks. The follow-up question is for 4 marks, and it asks us calculate the percentage of paper that is colored gray. Now, in our case, is colored green. The percentage of this paper that is colored green. Okay, now let's see, how do we find that percentage? That color green colors an area on the paper. Okay, now in this case, the area and the length of the strip is going to be the same because that strip is 1 centimeter high. So length times the height in this case gives us that area, but the height is 1. So in this case, the area and the length is going to give us the same thing in terms of what the area of that strip is. Okay, so we want to know. Now, let's think carefully here. 15 of these strips are not being used. So the number of strips that I'm using is over a height of 15. If you accumulate that height of each of those strips, it comes up to a height of 15. So half the page already is not covered with green, is white. Okay, it's a white piece of paper. Okay, so let's find out. How do I find the total area covered? So the total area that are covered green, let's make it green in this case, will be the following. It will be the first 21 plus the next one, which we've already got, 0.85 times 21, plus the next one, 0.85 squared, plus 21, times, not plus, what am I saying? Let me remove that immediately. So that's times by 21. Okay, and that continues. How many strips are there? In total, there's 15 of those strips. Now remember, the first one has a power of 0. That's the catch. The first one has a power of 0.85 to the power 0. So 1 was 0. So 15 is going to be a power of 14. 0.85 to the power of 14 multiplied by 21. Now, folks, that's the total that is covered. And remember, we actually want the percentage that is covered. So let's find this sum. This sum will be, if I break it down, 21 times 1 plus the 0.85 plus 0.85 squared, and it continues up to 0.85 to the power of 14. And we can all see, folks, because we're multiplying, this is a geometric sequence. The first term in the sequence is 1. I removed the 21 to simplify our work. Now, all we need to find is the sum of that square bracket. So this becomes 21. Now, remember, R is your R value here is 0.85, which is smaller than 1. So we're going to work with our formula 1 minus R. Okay, so the first term in that is A. So 1 multiplied by 1 minus R, and R is 0.85. Okay, 1 minus R to the power of n, and the n in this case represents the number of terms in the sequence. There's 15 terms. Don't fall into this trap and put a 14 there. There's 15 terms in this sequence divided by 0.85. Now, folks, 1 minus that 0.85. It's 1 minus R. So what did I apply there? Let me put the formula on the side here for you. We worked with Sn, which is A, 1 minus R to the n over 1 minus R. A was 1. 1 minus R is 0.85. N is the number of terms, 15, divided by 1 minus R. And this result is a 1, if you put that into your calculator, 127.770.4093. Now I'm deliberately keeping all those decimals. So that's the total area that is covered green. Okay, this is the total area. Total covered green. They want to know what percentage of the paper is covered green. Okay, so we've got that area. We now need the area of the paper. Okay, so the percentage covered will be the area of our paper, and the area is 21 multiplied by 30 is our whole. That is the total area of the paper. And what do? We multiply this answer with 100 to turn it into a percentage. So we have 127,770, the whole number, divided. So the part over the whole multiplied by 100 gives us the absolute percentage that is covered here. So finally, the percentage covered will be 20.28%, correct to 2 decimal places, is covered green. Okay, so it's a nice application question. Let's quickly just run back to it. It covers a piece of paper in which every second line is skipped. So there's nothing drawn on that line. So already we've cut the paper in half. 50% of the paper is used. Okay, and then every time we put a bar in, the consecutive bar is 85% the length of the previous one. So there's a geometric sequence developing. And because there's 30 centimeters, each bar is 1 high, that means there's 15 of those bars that are colored green in total. Okay, folks, so that was quite a nice question. A little bit of a challenge for a change in terms of our sequences and series. I see I've got just over 12 minutes left, folks. So let me wrap up with a question that is an application. These are usually very, very, not necessarily difficult, but tricky questions that comes up in the calculus section of your paper. Okay, so I'm going to look at the graph that I've got here. The graph goes as follows. We've got an x-axis, we've got a y-axis drawn. On that graph, we have this. This is what they give us. They tell us that the function that we're looking at is y equals x squared plus 2, where x is positive. Now, when I saw this graph in the initial, I thought, why did they not give me the y-intercept? And then I saw that we have the function. So we have the y-intercept. The y-intercept is the constant in the equation, which is 2. Now remember, you'll see this is not drawn to scale at all. Then somewhere here on my y-axis, they give us a point. And they say that is the point B, and the coordinates of B is 0 and 3. Now, the context of this graph. This graph represents a motor car that's traveling along the function. An observer is at point B over here. He's observing the car traveling. Now, let's just say the car is over there at the point, okay, at the point where he observes it, it's there. Let me just move the diagram up. I just realized that you guys cannot see all of this. That's better. There's the B. Okay, so now they're asking us to find the closest distance that these two are apart from each other. So here's the vehicle, the car, here's the observer. They want, when he observes the car, when the car is the closest to him on that trajectory. Now, we need to form a problem here. So we start and we put the variable point. Remember, C is the car that's moving. So we put the variable point on that path, and we need to work with variable coordinates. Now, folks, remember what this is. This is an x, y coordinate. X is independent. Y is dependent on x. Do we have y in terms of x? And yes, we do. There it is. So we're going to work with the coordinates of C as the coordinate pair x and x squared plus 2. And the coordinates of B is fixed. And that's the distance. We want this distance to be a minimum. So the question is, he observes the car when the car is closest to him. Okay? How far is the car away from him? Now, it's not to say that that is going to be the point. The point can be somewhere down here. I don't know. But we introduce it deliberately in variable form. Now, remember this relationship. If you have the equation of a graph, you have the relationship between the x and the y coordinates on that graph. And this is what we're working with. We're working with that relationship. Okay, so we need to find an expression for that distance BC. I'm going to square it for now so that we don't get stuck with a square root and get intimidated by that square root. Okay, so BC squared, distance formula, is x minus naught, which is x squared, plus this x value here is x squared plus 2 minus the y value there, minus that y value, all squared. Now, please don't be intimidated by these powers, folks. They only represent the distance that these two, the body and the car, are apart from each other. So x squared plus 2 minus 3 turns beautifully into x squared minus 1 all squared. And now we've got a square. So x squared plus x to the 4 minus 2x squared plus 1. Okay, we can clean it up. We can combine those two terms. So we have x to the 4 minus x squared plus 1. And that is the representation of that distance squared. Now, I'm keeping it squared because I absolutely don't have to work with the square or the square root. I work with what's underneath that square root. So if I had the square here, the square root, it would have been BC is the root of x to the 4 minus x squared plus 1. Okay, the point here is I do not need the root. I need to optimize what's underneath that root. And then finally, when I find what this actual distance is, then I bring the root back. Okay, so let's focus on optimizing this length over there. Okay, so what do I do if I optimize that? I differentiate it with respect to x. So I'm going to differentiate for x to the 4 minus x squared plus 1. And that result is going to be equal to naught. Why do we make it equal to naught again in calculus? Remember, a derivative is naught where the tangent is horizontal. Okay, because the gradient there is horizontal. Tangents on graphs are usually horizontal at local maxima or local minimum points. Okay, so if I optimize it, I'm looking for a zero gradient on the graph of x to the 4 minus x squared plus 1. That's where the optimum lies. Okay, so let's continue. If I differentiate that, I get 4x to the 3 minus 2x. The derivative of the constant is 0. That is equal to naught. Okay, now remember, I'm after that x value. that makes that naught. Okay, x can it be naught? Well, let's see. If I divide the 2 away and I remove an x as a common factor, I'm left with x squared minus 1. Remember what happened? Let me do that slowly. That cancelled. I divided everything by 2. The x was out. I thought I'm going to leave that 2 out. So here we have 2x squared minus 1. Okay. So now let's see. If I go up here, I have x times x minus 1, x plus 1, which is naught. So I'm only looking for positive x's because the initial question said I'm only working with x values that are bigger than naught. Now that is key here. X cannot equal naught, and x can also not equal a negative answer. So I'm going to ditch this answer and that one. And again, look at what I did. I left the 2 behind. So we have a root 2 there and a root 2 here. Let me just fix that one. It looks silly. Okay, so that's the difference of 2 squares over there. If I find the factors of the difference of those 2 squares, I get x root 2x minus 1 and root 2x plus 1, which is naught. Okay, x we discounted can't be naught, and this one we're going to throw away because if we solve it equal to naught, it becomes x is minus 1 over root 2, and we're not allowing for negatives. So what is x? X is finally 1 over the square root of 2, and that is because x is only positive. Are we finished? No, we're not. The question says, what is this minimum distance? Okay, so now my minimum distance is the square root of this thing to the power of 4 minus the same thing squared, and I think it was a plus 1 under the root. Yes, it's a plus 1. Okay, so now let's see what we have. If we raise 1 over root 2 to the power of a 4, we have a quarter. Okay, so here we get a quarter minus 1 over root 2 squared gives us a half plus that 1, and that leaves me with 3 over 4 inside of that root. Now, folks, that is the distance that they are apart. Now, here you must read your question carefully. If they say give the answer correct to 2 decimal places, then we're going to calculate that answer. If they say leave the answer in simplest surd form, all you need to do is you need to take the square root of 4. So that's root 3 over 2, and the units they gave us was kilometers. So BC is that amount of kilometers, so therefore the car, always answer the question, the car is root 3 over 2 kilometers away from the observer at point B. Okay, that was a calculus question. Now, what was intimidating here in this particular question, folks, is the fact that you had to work with a distance formula. The distance formula has a square root over it, okay? And that square root does not matter when I'm trying to find x. They've asked this question many times in the past, and people leave it out because they think, oh, but I can't differentiate over the square root. I can't do that. You only work with what's underneath that square root. We could have completed the square if we wanted to. Okay, there's many ways to answer this question. But remember, at the point where you're finding x, I worked with the BC squared so that I can avoid that actual root. Once I had the answer, I plugged it back into BC, and that gave me the distance that these two bodies, the car and the person, are apart from each other. Okay, folks, that concludes our show for today. Your first paper is usually the paper where you should get better marks in because it is based on algebra. There's a little bit of probability in the paper. Most of the first paper is algebra. So please make sure that you know your algebra, you know your processes involved in the first paper.